In this video, we'll be considering the analysis of circuits in the context of working with microcontrollers. Let's start by looking at resistors. The fixed resistors that we have in the microcontroller kit are 4-band resistors. That is, they have 4 colored bands on them, and each of the colors is associated with a specific digit. So the resistor that's shown here has 4 colored bands on it. They are from left to right: blue, red, black, and gold. And so we can see from the chart that the first digit and the second digit are specified by the first 2 bands, and then the third digit is a multiplier. It's a power of 10 that's associated with the digit. And then the fourth is a tolerance. This particular resistor shown in the example has the digits 6, 2, and then black corresponds to 0, which means 10 to the 0 power. And then gold, the tolerance band, is plus or minus 5%. So what that means is that we have a resistor that is 62 times 10 to the 0 power, where 10 to the 0, as any number raised to the 0 power is 1. And then we have plus or minus 5%. So the resistor that we're looking at here is nominally 62 ohms, and then it could be up to 3.1 ohms higher or lower than 62, which means that the range of possible values is 58.9 up through 65.1. So the manufacturer of this resistor guarantees that the resistance, the true resistance of this resistor, falls within that range. And that's how it is. When you get resistors, they have a nominal value, but the true value is one that you would have to measure to actually find out what it is. So now let's look at another example. So let's say that we have bands brown, black, orange, and silver. And again, this is a 4-band resistor. We see from the chart that brown corresponds to 1, black corresponds to 0, orange is 3, so that means 10 to the 3rd power, or 1,000, and then silver is plus or minus 10%. So that means that this resistor is 10 times 1,000 ohms plus or minus 10%, which is 10,000 plus or minus 1,000. So the particular resistor that we're looking at right now could be anywhere between 9,000 and 11,000 ohms, which is quite a range. 10% tolerance isn't all that great. There may be some situations where we don't mind using a resistor where the value could be so varied, but in most cases we'd like the tolerance to be a lot lower than that. How do we find out what the true resistance is of a resistor? We can use the multimeter on its ohm meter setting. So in order to look at resistance, we need to consider all of the settings that are along the sort of the southwest and south side of the dial. The settings that are possible range from 200 ohms all the way up to 200 mega ohms. And as is true when we're looking at using the multimeter as a voltmeter or an ammeter, and we have these various settings, what we need to do is choose the setting that has the highest possible precision. So for example, if we're measuring a resistor that is nominally 1,000 ohms, and we'd like to get its exact resistance, then we need to put the setting on 2,000 ohms. We need to choose a setting that's higher than the nominal setting or the expected value, but not too much higher. We want to pick the lowest one that's higher effectively, and then that way we'll get the most accurate reading. Now, to actually measure the resistance, the multimeter acts as a voltage source. So this means that when we're measuring a resistance, we don't want to have the resistor actually connected to anything in a circuit. We shouldn't have the power on. We can use the breadboard to stick the resistor into, but it should not be attached to a circuit. And we want to make sure that the ends, the wires, are not in the same row. Okay? But we can actually put it in, and then it will be held steady. And then we take the leads and put the probes so that they are touching the wires. on either side of the resistor, and we can measure the resistance that way, and then get the true resistor value. So what you might want to do is take a 220 ohm resistor, maybe one that you've been using to build the blink circuit, for example, and measure the true resistance, and do that as an exercise and find out if it does fall within the range of tolerance. Figure out what the range of tolerance would be, the allowed values or the stated values according to the manufacturer of what the resistor could be, and then find out if the value falls within that range. Now let's look at some circuits again. So here we have a circuit that's very simple. It has two elements connected to each other by what we consider to be perfect wires. They are a voltage source on the left and a resistor on the right. Because there is a closed path, there is current flowing. IA is the current everywhere in this circuit, and it flows clockwise through both elements. We know, because we've already done the analysis, that the voltage associated with the source has to be the same as the voltage across the resistor. Now, when we have a slightly more complicated circuit, as shown on the right, we've analyzed this one as well. In this case, the current is I sub B, and it flows clockwise through the whole circuit. And for this type of circuit, we found already that the voltage across the source has to be the same as the sum of the voltages across the resistors. And both of these statements are true based on Kirchhoff's voltage law. Now, if we let IA equal IB, then it turns out that R, the resistor on the left, must be equal to the sum of the resistors on the right. They are equivalent. The other thing that's true is elements that are in series, like the two resistors on the right, are going to carry the same current. Elements are in series when they are joined together at a node, and there's nothing else that's there at that same node. So let's mark the nodes to talk about this. The nodes or junctions are where components are connected. So here on the right, we've marked 3 of them. There are 3 places that we have components joined. And we see that in each case, there are only 2 wires at the junction. That means that the current that flows through the junction has to be the same entering as leaving the junction. And this means that the same current is going to flow through any elements that are connected in this way. And so any elements that are connected like this, where there are only the 2 elements at the junction, are considered to be in series. The fact that elements in series carry the same current is something that we're going to be able to use to help us to solve circuits, more complicated circuits than these. It's also possible to connect elements in parallel. So let's start by marking the nodes here. Elements are considered to be in parallel when both terminals, both wires, are connected to the ends of the other element that an element is considered to be parallel with. So in this case, we have 3 elements, the voltage source and the 2 resistors. The top wire of all 3 elements are connected together, top wires, and then the bottom wires are connected all together. And what this means is, well, that they are in parallel, and we want to see what this implies. If we look at the path that's marked in red, then we see that we can apply Kirchhoff's voltage law here. We have a rise of V volts and a drop of V1 volts as we go around the closed path. And this means that V is equal to V1. That's not the only path that we could follow. We could also follow the outer path. And there we would find that by following this path, we would have a rise of capital V volts on the left and a drop of V2 volts on the right. And that means that V is equal to V2. Thinking again voltage as being like an elevation, if we start at the bottom of a hill and climb to the top, it doesn't matter what path we reach, it's going to be the same. So if I go up capital V to get to the top and I come back down to the same place I started by going through V1, then that means that V must equal V1, and similarly V has to equal V2. This also implies that all 3 of these voltages are actually equal. They're all going between the same points, really. They're the voltages across the same location. And in general, elements in parallel have equal voltages. We can use these characteristics of series and parallel elements, along with Ohm's law and Kirchhoff's current and voltage laws, to help us analyze circuits. Let's look at this more complicated example. So here we have a network of resistors attached to a voltage source. We'd like to design this circuit so that 2 amps will pass through the 6 ohm resistor. So we'd like to figure out what voltage we should have for Vx to make that happen. The first thing we do is we identify where all the nodes are, where all the elements are that are connected. Then let's look at what we know. This is kind of like solving a puzzle. We see that we have a 6 ohm resistor and that 2 amps pass through the 6 ohm resistor. Well, the convention that we use is that current enters into the positive terminal of a resistor because energy is dissipated there. So we expect a voltage drop across that resistor, and let's call that voltage V1. Ohm's law gives us the relationship between voltage and current in a resistor, and here we see that we can use Ohm's law to find out what V1 is, since we know the resistance and the current. We can say that V1 is 6 ohms times 2 amps, and that gives us 12 volts. Then we notice that the 6 ohm resistor and the 12 ohm resistor are actually in parallel. We see that both ends are attached to each other. That means that V1 volts, that's how many volts we have, not just across the 6 ohm resistor, but across the 12 ohm resistor as well. And that means that we can find the current in the 12 ohm resistor. We can use Ohm's law again. Here, again, we're going to say that the current is entering the positive terminal of the resistor, and then we can apply Ohm's law to solve for I1. And we see that I1 has to be 1 amp. Then we notice, by looking at the node that's in the center of the circuit at the top, there are 3 wires connected there, and we know the currents in 2 of them. We can find I2, that third current, the current in the other wire, by applying Kirchhoff's current law. We know that the currents entering the node, that would be I2, has to equal the sum of the currents leaving. That would be the 2 amps plus I1. Since we know what I1 is, we can find I2. I2 is going to be 3 amps. We also see that I2 must be the current that's flowing in that entire wire through not just the 3 ohm resistor, but through the voltage source and the 2 ohm resistor. So that means that we can specify I2, the current, through the 2 ohm resistor. We can say that we know that the current is flowing right to left. Nope. Yeah. Right to left, exactly, through the 3 ohm resistor, and that means that we can designate the positive terminal for V2, the voltage across that 3 ohm resistor. And then given that we know that it's 3 ohms and that I2 is 3 amps, we can solve for V2 and say that it's 9 volts. Similarly, we can find the voltage across the 2 ohm resistor. Again, the current enters the positive terminal of the resistor. So we can find V3, and we see that it's 6 volts. So now we know all of the currents in every wire in this circuit through every element. We know all the voltages except Vx. So to solve the circuit, that is to know everything about it, we just need to find Vx, and then we'll know the currents and voltages everywhere. We're going to use Kirchhoff's voltage law to find that voltage. The sum of the voltages around a closed path has to be 0. So as long as we choose a path that includes Vx and it's a closed path, we should be able to solve for it. So let's choose this path that's marked by the purple dashed line. We'll begin in the lower left-hand corner, and then we will sum the voltages, moving clockwise. First we go up, passing through the 6 ohm resistor. There is a rise of V1 volts. Then we pass to the right across the top of the circuit. There's no change in voltage along that wire. Then we go through the 3 ohm resistor, and there's another rise, this time of V2 volts. Then we turn the corner and go down through the source, Vx. There's a drop of Vx volts. Then we get down to the bottom, and then we move to the left across the bottom of the circuit, and we pass through the 2 ohm resistor, and there's a rise of V3 volts. And then finally, we go along the wire all the way back down to the lower left-hand corner, and along that wire, there is no change in voltage. We can express this as the sum of V1 and V2, because those are voltage rises. And then the voltage drop that we experience as we pass through the resistor, we say that's we pass through the source. We say that's minus Vx. And then there is another rise of V3. And that whole sum has to equal 0. So that's the way to describe the rises and falls of voltage as we follow that path. We know all the values of the voltages except Vx, so we can just insert the values and then solve for Vx. And Vx is 27 volts. So this is a step-by-step process. Obviously, there are a whole bunch of steps, but we take a result and we use it to find the next parameter, and then the next parameter, and next the parameter. And so it's really quite systematic. It's like solving a puzzle and using the information as we go and these principles to solve the entire circuit.